Hello, can you hear me well?
Yep, we can hear you.
Hello, can you guys
Hi,
hear me?
Kapil.
Hey, Carmen. Okay, so we have 33 attendees. Should we begin now or wait for a while, Carmen?
Yeah.
We're only like a minute away, so up to you.
Okay. Right. Max says go for it. I think we can wait for a minute, just to be fair. All right, I think we can begin. Acha, should we go for it?
Yeah, let's go for it.
Okay. Hello, folks. Welcome to the second day of Clojure North conference. This is the Concurrency Workshop. It's going to be a little longer, but we promise we bring a lot of interesting things along the way. Most of our workshop material is based on practical or like engineering based problems that we'll solve one by one. The nature of the workshop is going to be slightly interactive. So we'll like talk about that in a bit. About myself, I'm Kapil. I work at HelpShift. I've been doing Clojure for more than 8 years now. Aricha, you wanna go next? Introduce
Yeah,
yourself.
yes. First off, I think thank you, Nick, for getting both of our names right. I think
Yeah, that's really
a
hard.
job well done.
Thank you.
Yeah. So I'm Rhishikesh Joshi. I've been working at HelpShift for the last 9 years, probably. And since all of our backend team, so I am primarily a mobile developer, but for the past 8 months, probably I've been writing Clojure code. And since I've been around folks who have written production systems in Clojure, and we have had long discussions about how type safety and dynamic types and stuff like that. Uh, so yeah, I've been a Clojure language warrior for a long time, I would say. So yeah, and serendipitous thing is, so my interview at HelpShift was a programming assignment in which I had to write some Go code, and it had
Yeah.
to incorporate a lot of Go channels and concurrency in CSP. I think Kapil had reviewed my code.
Yes.
So I'd say, almost 9 year full circle for me. So yeah, looking forward to the workshop now.
All right. So let's get started. I'll start by sharing my screen. Maybe I'll turn off my camera because internet here is a bit of flaky. Okay, so first things first is the workshop is going to be like interactive. So I'm going to ask a few questions saying, hey, what do you think about what is concurrency, things like that. And we'll start with that. What I want everyone to do is I'm going to start a Slack thread on concurrency with Clojure channel. And this is going to be for the first chapter, and every hour is more or less like one chapter that we have divided, and each chapter is a namespace in the repository that we have shared the link to. I'm going to share just create a new thread and want everyone to just reply to that thread when I like ask questions or like ask for like saying, can we go forward, has everyone solved this particular problem, and just uh, if everyone is on that thread, that will be very helpful. Also, this is because Zoom does not have history for its chat, so it's better for new people who are joining in to just look at the Slack thread and catch up. Let me ping that discussion. All right, so just to test it out and start off the workshop, first thing I'm going to discuss is just concurrency, right? What does everyone think about concurrency? What is their experience with Clojure, and just just a one liner about like what concurrency means, and we'll take it from there. I'll wait for responses. Trouble. Okay. Doing more than one thing at a time. Yeah. Over engineering opportunity. Doing one thing the wrong number of times using multiple CPU cores. Okay, so ideally making optimal use of multi-core system, doing stuff out of order. Okay, there's one question by Louise. Parallelism versus concurrency. We'll talk about that also a bit. Accidental complexity. Jordan, I love that reply. Oh, Maximilian, I am sorry. But like Python also has its advantages. Core async works in Clojure scripts. Yes, multiple things at same time. So basically, there is this general notion of doing multiple things at the same time, right? That's what we want to do. Just to like even formalize that even more, basically concurrency means concurrent access of multiple threads or multiple actors or multiple places to same place or same database connection or same file, right? By that logic, you are just saying I want a safe access to something and I want to write or read from that common location, right? Now Clojure provides immutable data structures, and which means there is no mutation, so that's great for concurrency. But even after that, you have to like change things at some point. You have to have shared values for some problem statements, and we'll look at that. But first we'll also look at a few different paradigms of concurrency. The typical concurrency pattern that we have learned is pessimistic concurrency, where you use locks. I think very visually, so I have like gotten a visual representation of concurrency with locks from the internet, and I love dogs, so yeah. So I'll just let that GIF repeat again. So this is kind of how locks work, right? They are like trying to get hold of the common shared resource and do their work and move on, right? Uh, so, hey, Rishikesh, can you see the screen?
Yeah.
Okay. So I'm going to share.
Go on. Sorry, I'm still seeing your GIF. If that is what you're.
Yeah. So this is, I'm just talking about like how concurrency
Yeah.
with locks works, right? The way STM works, will like watch. There's also a visual representation of that, but we'll go there in a bit. And I'll switch to my Emacs editor so we can walk through the code. All right, so we have gone till the part about basically mutating things, mutating values which are read or written by multiple threads. There are 4 ways which Clojure allows you to do that. Of course, we know about atoms, agents, refs, but vars also, technically you can like mutate things. You can say that, okay, now this vars holds a new value. So we'll consider vars also and look at it from the standpoint of concurrency. But first, when we say concurrency, we need threads, right? To have like access from multiple places. The simplest way to create threads in Clojure is future, right? So when you run future1, it results in something called hash future. It has the value 1. The way you read anything that is resultant from a future is with a deref. So when you say deref, it just results in 1. A shorter form of deref that is supported by Clojure reader macro is at, which does the same thing. And deref is like a very interesting abstraction or interface which lets you like read things that are in transition. Now we'll see how deref works with other constructs also, but for future derefs work like this. Another interesting thing for deref is the values that are derefed. Let's say I run this future and I am like storing it in a var called f. Now first time I run this future, it will print running thread and result in 1. The moment I deref this, running thread won't print again because that value is cached now in f. The same way, if I run this again, it will just return 1 and nothing else. Okay, so we got till the part about understanding futures. And I want you to like just as a checkpoint, I'm going to do this is put out all good so far, and you can just reply with a thumbs up on this. This is just testing. I won't like go so slow, but this is just for us to figure out communication lines. All right, so moving on, there is another construct called promise. What promise lets you do is uh, basically talk between threads. So when you say define a promise like this, and this is also a thread which is your REPL, and then you create another future and say wait for 5 seconds and then deliver a value 1 to promise P. Now I have added a thread sleep of 5, and if I try to deref this P, let me run this again. Now this deref is blocking. The reason why it's blocking is because there is no value that is there yet in that promise. And if I create another new promise and just deref it, it will just indefinitely just be blocked until a value is delivered to it. This is just semantics of a promise. This has nothing to do with deref. Deref is just says give me the current value. It just so happens that there is no value for a promise to deliver, so it just blocks forever. All right, so we looked at future and promise. Now we'll look at the most basic thing that we don't even like think about it from a point of view of concurrency, which are vars. The simplest thing you can do with vars is you just define a new value to it, just def x1. And these values are accessible by different threads. So if I run this whole thing, A will be printed twice. Nothing to see here, and it's pretty basic. Now, before moving to atoms, right? And atoms are used to represent shared state and also change state without creating a lot of mess. But when we say mess, right, we should also understand what is this mess in the first place and what are atoms doing so special. So what I'm going to do, and this is an example from Afir's blog post on state, and this is an amazing blog post. You should definitely read it thoroughly. But for now, we'll just translate whatever this Java code is into a Clojure counterpart. Now, first I'm going to ask a question about this, and you can again reply on the thread, is if I run this do, there are going to be two prints. What is the value of this print? Is it going to be 3, 4? Is it going to be just nil at sometimes, or is it going to be 4, 4? I'm going to not do this and just ask for what everyone feels the answer is. So James, you are right. The answer would be 4, 4. And here we can always try this out in the REPL, and REPL will give the most correct answer. The idea here is we are trying to build an intuition about concurrency constructs in Clojure. So try to maybe like figure out the answers just by looking at it and do some guesswork. That will just like help you create a better mental model of how these things are working. So if I run this, this has printed 4 and 4, and this is great. The next one is pretty interesting, and I want everyone to like take a guess without running this in the REPL itself. Is what does this print of count of B will return? Now, what we are doing here is we are saying B is a empty vector. Then we are running a do seek of 2000 elements, and every element is firing a new thread, and that thread is saying take the current value of B and conj the element in that. So what should be the answer here? Okay, Luis is saying 0. Okay, James. Promise not to like share it here then. Okay, one few of the answers are 1. So here it's interesting to note that we are yeah, RHI's answer is also amazing, which is 42. Uh, all the futures, let's say we add a thread sleep here just for the futures to like catch up. So we add a thread sleep of 1 second. So now all the threads have done their work, mostly because Clojure is fast and going through 2000 elements should take less than 1 second, right? So should the count of B should be 2000 or 0 or 1? Any takers for 2000? Okay, Stephen is saying 2000. That's a very interesting question, Nathan, and we'll look at it in a bit. Bang on, James. It's less than 2000. Somewhere between 1 and 2000. Yes, Nick, you're also right, and probably not the full 2000. Yep, yep. So let's run it now. Uh, yes, it's also not in order also. So let's try it out. Wesley, I also have Slack running on it, so I'm not sure how many CPU cores are actually being used. Okay, so we have this answer 1941, which is saying, okay, the count of B is 1941. Let's run it few more times. 1867, 1859. So we can see something odd is going on here. And I think most of you have answered correctly saying that it should be between 1 and 2000, which is the right answer here. The only determinism we have is it will be either like more than 1 and less than 2000. Okay, so let's ask ourselves, why is this happening, right? What's going on? So what we can do here is we can slow some things down. So we have similar kind of code on the next code block, which is B is an empty vector. I'm going through 2000 elements again, but what I'm doing now here is I'm saying at the fifth element, print the count of B, sleep for some time, and then do your work. Okay, so I'm going to run this. And what's happening here is I'm getting count of B as 6, even though all the threads are doing their work and there are 2000 elements. And the answer is going to vary bit by bit. It's going to be 3, 4 sometimes, it's going to be 5, 6, and it's going to keep varying. The reason here why this is happening is by the time we reach the fifth element, right, whatever the value of B is, okay, it's frozen. Then we are saying, okay, sleep for 100 milliseconds. By this time, rest of the threads have done their work, right? And then we are saying, okay, what was the last value of B? 5. Just conj 6 on it because we are saying just add more values. And then we have like corrupted data, because we have not saying take the latest value of b, what are like what is updated by all the threads. Just take the last value that you have seen during your thread run. And that is the problem with vars, is that it won't take latest value. Also, another way to put it is it will not handle collisions. It's not aware of the collisions at all, right? And that is why we can't use vars in any concurrent scenario, right? uh, okay, I'm going to again ask all good so far. I wait for the thumbs up and move ahead. All right. So let's introduce atoms, right? So the way to define an atom is just like how you define a var, you are just wrapping it inside a atom as expression. Interesting thing to remember here is Arnold, I'm just waiting for the thumbs up to stop for a while and then go ahead. I'm mostly waiting for a thumbs down so I can go back and like just explain a few things. If I get majority of thumbs up, I'll just go ahead a little bit. And if I'm going slow, again, you can just ping here and I can go faster. Okay, so we are like, oh, there was a thumbs down. All right. So now we introduce atoms, right? And we again introduce our dear friend dref. I define an atom, it is holding a value 1. Interesting thing to note here is values held by an atom should be immutable. Okay, and this is something that gets you by surprise at times if you don't like hold those values, because all of the underlying concurrency mechanisms assume that all the data structure that are used here are immutable. Okay, so we have value 1 in A, and now we can deref, and it's 1, shorter form, again 1. Okay, so let's try our example, but first we'll need to know how to mutate a value of atom, right? Another way of doing it is like vars, but that's not how we are going to do, because we're just going to say we are like redefining the var and not changing value of atom. So the way you change atom's value is by saying swap, or you can just return a function. Here I'm just returning constantly 5. If I read this, the value is 5. Now, going back to our example, the one we have tried out with vars is just hold a value, hold a empty vector in B, run the 2000 things in a thread, and then count the value of uh, count the B vector and print it. Okay, so I think everyone knows the answer here, but just like for sake of completeness, let's like take answers first without running it on REPL. Yep. James, I trust you haven't run it on REPL yet. Yeah, so answer is 2000. And the reason here being that we have this now semantics called swap bang B, and that enables you to set to the latest value, right? Even if there is a conflict or there is collision, atom is smart enough to know that collision, and they will like make sure that the data is not lost. Yeah, and one way to say that is compare and set. Uh, sure. Uh, who wants to take a guess that will they be in order or not? Does this okay, we can also ask that, does this guarantee order at all or not? Yep, that is correct. Order is not guaranteed at all. Is going to be approximately order just by the factor of all the futures are running in one after other sequentially, and hopefully they'll get picked up in order, but it's not guaranteed. So if I print B itself, and I'm going to reduce the number of elements here so my REPL doesn't blow up. It's somewhat in order, but like this outer order is not guaranteed, right? Because like all atoms are doing is they're making sure the conj happens, right? They don't have this or notion of order itself. They just have notion of what was the latest value on this b and just apply new functions which are swaps on the latest value. If you count this b again, it will be 100. All right, moving on, we can go ahead on refs now. Before I go to the refs part, so atoms are basically used when you don't need coordination. Another way of saying this is you have single register values, which means you are just updating one place and one place only, and you don't need coordination between two registers. When you want coordination between two places, that okay, set this value and also set the other value. If one of them fails, don't set anything, just like a database transaction. Now, this is allowed due to STM, which is software transactional memory, which is implemented in Clojure. Again, visual reference. I'll go to my browser and show everyone how I imagine STM works under the shell. This is a animated video. It's not real, but this is something that we see every day in India. This is traffic in India, but like this is composited, so don't worry, this did not happen in real life. The point here is if you were to draw parallels to STM, basically that's what we are doing. We are doing optimistic concurrency, assuming that everything will run, right? We are saying that, okay, go ahead. If there is any collision, literally so in this case, just reverse time and try again, right? That's what we are saying. All right, so now we have some understanding of like kind of some intuition of how STM works. We'll go ahead and like try out refs. Okay, so we have now two registers, as I mentioned. One is a ref num and other is b ref num. I define these. Now here, what we are doing now is we are saying that I run it 10 times in a thread, in a different thread in a future. This is how you define a transaction where you are saying do sync and set these values. Set a ref num to n and set b ref num to n. What this means is if you are setting a ref num to 1, you are guaranteed to be having the same value at b ref num. If another thread tries to like write a ref num to 2, meanwhile b ref num is being set to 1, it's not going to let you do that. It's going to say, so in a way it is saying any value set in this transaction, it is going to be same for a ref and b ref, right? So we are going to run this. Okay, so there are a bunch of transactions that happen. And if you see, I see prints for the same value again and again, because what has happened is since these threads are running concurrently, there is going to be a collision, and this do-seek is saying, okay, there is collision, let me try again. Now again, not running this in your REPL, what should be the value of this a ref num and b ref num when we deref them? Is it always going to be 7 and 7? Yep. So James is correct on this one again, is the values are 7 and 7 or any same number, right? The reason being that refs transaction semantics guarantee that both the values are same. So if you deref them, it will be just the same number, 7 and 7, but it's not always guaranteed that it will be 7. Yep, that is correct, Dan. It depends on which transaction finished last, and that is the value it will get assigned to. We'll try this again with atoms and refs. what we are doing here is we are running again 100 threads. We are saying set value to aref and bref. We are adding a sleep in between, right? This means this transaction is going to take a lot of time to complete, and this is not something that you will do ever in production. This is the same reason why you don't do IO operations also in a do sync, because what you want to do is get this transaction done as fast as you want. If the transaction is taking too much time, it means there is going to be contention, right? So you want to avoid contention as much as you can. Also, this means that in a high contention application, maybe using STM is not the best case, but most of the application that we built, there is not going to be a lot of contention. So let me run this and let's see how this prints it out again. Okay, so there are going to be 100 threads that are running. Then I'm going to meanwhile print the values of aref and atom every 1 second. All right, so what is happening here is we are saying ref values are always equal. Looks like atom values are also equal in this first print, but it's just a coincidence. Next time, for the next second, when we print aref and bref, they are again same, but atoms are diverging now because more and more threads have been spawned and they're trying to edit atoms as well as refs. But refs are guaranteed to be same, so they're going to be same. If you want to be really adventurous and slow down your machine a lot, what you can do is add like a bigger thread sleep, like 2000 seconds, 2000 milliseconds here, and this will keep retrying this transaction forever because there is going to be a lot of contention. Please don't try it, but just for experiment, if you want to run it after the workshop, you can. So this is the end of first chapter. I think we are good just using the same thread for the second chapter. In second chapter, what we are going to do is build a solution to thundering herd problem. I'm going to open up the second chapter's page.
Kapil, you want to use the same thread for the
Yeah,
second
yeah, let's
chapter?
use the same thread
Okay.
because this is working out, and I think just create too much noise again on the second thread. Anyone wants to give it a go about like trying to define thundering herd problem if they have like faced it on production? Oh, okay. Sure, sure. I missed a question. Let me go back in the thread and see. Are all refs under the same global transaction lock inside a two-sig block? Can we have a independent sets of refs? So Wesley, if I understand your question correct, what you are saying is in a do-sync block are all refs under like a lock, right? I don't know how to like talk about this. Yeah, yeah, we can create a new thread or not. Aracha, you want to create a new thread?
Yeah, I'll do that.
Oh, so your question is that can there be like two sets of refs? So let me type it out and maybe Wesley you can like reply on that. So you are saying a alter b alter c alter d alter. So are you saying that are these can these two sets of refs be independent of each other? Not really. So everything you do inside a do sync will like have some relation to it. either all of it completes or none of it completes. So when you referring to like any refs inside it, you are trying to edit it or like read from it. So it is treated as like one database transaction.
Kapil, Carmen is suggesting maybe we want to give them a chance to like talk here
Yeah,
instead
yeah.
of like.
Yes, that will be
So
really great.
either
And I can,
either one of Wesley or Arnold, if you want to just raise your hand, we can get you to speak.
yeah, I think Wesley can like definitely have
Yeah,
the
I think
mic right
Wesley
now.
is here. Yeah,
Hi.
yeah,
Are you able to
Hey
hear me?
Wesley. Yep.
yep.
Cool. Yeah, so I was just wondering if they're effectively a global resource across the entire JVM. Effectively, is there just one intersection if we were to look at the video again
Right.
that everyone uses regardless of like what's going on?
Not really, just the dosing part is you can look at it as an intersection at any given point.
Okay.
So I can
Yeah,
try to
please.
answer it. So think of a ref as a history of values that you are going to access, right? And the do sync is essentially a point in time where you freeze the history and you say that this is now what I'm going to read from the outside world. And inside the do sync, the only one who manipulates the history, right? And essentially, finally, when it comes time to commit, I go and look at the history and see if somebody else wrote after me. If somebody else wrote after me, it's a commit, like it's a commit time exception, and you retry the transaction. So
Transaction here being the dosing block, and
yeah,
that's why you
transaction
can't do
being
any.
the correct.
Yeah.
All right. So if one do sync block altered A and B and a separate one altered C, could they collide?
No,
No.
they don't.
And so they both run successfully, as it were.
Yeah.
Yes.
Sounds good. Thanks.
Yeah. You're welcome. All right. Should we, RHA, should we wait for a few more questions on chapter first?
Let me check.
Yeah, you can like
I
everyone
don't
just feel
see.
free to like raise hands if you have
Yeah.
any
Yeah.
comments
Yeah.
or any more discussion points on chapter 1. We'll wait for like 2 minutes and move on to the second chapter then.
Yeah. I don't see any unanswered questions as yet. I think. Yeah. You can wait a couple of minutes and move on.
Yeah. Yeah, I'm just going to use this time to like thank everyone to make this whole workshop process so easy. This is the first time I'm conducting a online workshop, and this feels like a breeze because the audience is so like interactive and helpful. So thank you for that. So Michael is asking, so what is the actual difference between a dosing block and a function passed to compare and set for an atom? So you can look at it this way: is uh, they are essentially the same, just that if you want to do the same thing with uh, two atoms, you can't do it, right? If you were to like pass a compare and set, you can always just pass it to one atom. But if you want to do coordination between two atoms, you basically want refs. Does that answer your question, Michael? Oh, great. Right, I think we can start chapter 2. Let me just put out the thread here. Oh, okay. There's one more question by Mark. What happens when we have multiple refs across multiple dosing blocks, for example? So there is a ref 0, ref set A to B, A to 2, B to 2, A to 1. Hmm. So Mark, here what will happen is when you have started to like set to V to 1, right? If value of A changes in between setting value of A to 1 and C to 1, something changes. Let me just put it in editor, and like that will be better to explain. Say there is a long pause here where I put semicolons. Okay. And during this time, A gets set to 2, just during this time, right? This whole thing will be repeated. You can try it out also. Println A transaction second running dot. Let's hope there is contention. Oh. Let's try out A, B, C. But there was no contention. Aracha, you want to give a go at it? This one?
Yeah, so what you're doing is ref set A, ref set B, then you're setting ref to something else. You sleep. So essentially one of the two is going to retry.
Yeah.
What is going to happen. So,
but in this case, this is retried. This is not even retried. This is just setting it as it is.
So it may not have contended, then that is probably the only thing. So maybe running it multiple times will cause it to contend.
So Mark will revisit this question again, maybe at the end of the workshop. Does that sound good? Yes, James. STM is optimistic. Oh, there is one more example. Okay, he's just doing the same.
Yeah, he's just given us a better version. Yeah. So also to answer James' question, correct. There is no conflict on C because there is no write from anybody else, anywhere else on
correct
on C.
Yeah. Okay, let's try to run this one again. It's 1, 2, and 1, which is B is set to 2 because B was changed here, and this one just got retried, and both are set to 1.
Yeah, I think one of you will always see one of them succeeding, and then that will be the value of A. And
yeah. If you like delay it completely, then value of a will be different here.
Yeah, correct.
If you delay it something like this, uh, not really.
I think do it in the do sync rather than outside it.
Here, right? But
Any delays have to.
then this will be 1 again. We have to do it here.
Set v to 10, like that will give us a different value. Set v to 10 and then add a thread sleep in the
This do
anywhere
sync,
will
right?
do. No, but यहाँ पे, like here we are not using v. Sorry.
What just happened?
Uh, do the same thing in the block below,
Here,
because
right?
in the upper block we are not using v. So set v to 10 or something. Yeah.
And let me run one without thread sleep. So here answer is 2 to 0. Let me just go through this during the break. We'll look at this mark again. I just need to like read it through properly. I need to deref futures in order to guarantee both finished. Not really. We don't need to deref futures because they are running. We can add a println. But let's hold on to this problem. I'm going to write this down in chapter 1 and we'll revisit this. Chapter 1, to-dos. Hardcode. Yeah, that's one hard coding over there. We'll try to look at it again. Shall we move to the next chapter? I'll just start the thread again.
You want me to do that, Kapil, or you're doing it?
Yeah, I'm just tracking it. All right, so the next chapter we are going to look at a real problem which happens with databases and cache layers called thundering herd. What thundering herd says is that if you have a database protected behind the cache layer and let's say that cache is not warm or like it's just timed out at the wrong time and there are lots of concurrent requests for the same key, all the requests will go to your database. In this case we have written MongoDB, uh, and in process we'll just overload that database, right? So here what we are assuming here is there is a database called MongoDB, there's a cache layer uh, which being Redis, and there's just one server that is trying to fix this thundering herd problem, right? We are not talking about like fixing it for multiple nodes and that goes into the realm of distributed systems, but we are just talking about, okay, if there are concurrent requests for the same key to our server, how can we protect our upstream backend dependency, which is MongoDB. Now here, if you go into the source code of db.redis and db.mongo, they are just like functions with thread sleeps in them, and they're trying to emulate MongoDB and Redis. So you don't actually need any of these dependencies to run this code, but it will just try to emulate what the problem statement is, right? For first, we'll look at how it's supposed to behave and how thundering herd problem will occur and how this will handle. So this is our read plus update 1, where what we are trying to do is read from Redis. If the entry is there, we return it with v and key Redis because we want to know where it was read from. If the entry is not there, we are reading from MongoDB. We are saying, okay, since you are while you are at it, you got the value. Also set the value and return the value to the caller, and also mention that this is from MongoDB just for our record. Now, if you run this on 10 requests, I've done range 10 and just run this on foo. Okay, this is not the right namespace. So what has happened is there are like 10 total requests. One of them went to MongoDB and 9 of them just went to the cache. Here what I'm doing is the Reddy's database here that I'm emulating is just an atom. I'm just resetting the cache entries to say that there is nothing in the cache. Now this is great, right? This is solving Thundering Herd problem, which is that only one request should go to your database and rest of the requests should go to your cache layer. But these requests are serial. They are not concurrent. They are happening one after other, and that's why we get the ideal effect. So I'm going to ask, is this problem statement good so far? Okay. So if we want to create concurrent requests, all we have to do is call them in a future. So they are out of order. They're just like, maybe they are like overlapping each other. And we are calling this read plus update function again with value key foo. Now let's run this whole do block again. Again, we are resetting the cache. So we want the same effect again. Here I'm doing one more thing is I'm derefing the futures. So I get the actual value. And then I'm running the frequencies of what is the distribution of the queries. Now, if you see, out of 1,000 requests, 615 went to MongoDB and just 385 went to Redis. Since we have a cache layer, it's safe to assume that this will take our MongoDB down maybe like this if you multiply these requests by a few thousand. So this is bad, right? And how can we solve this just with Clojure concurrency constructs? So we'll like take a one-step approach and we'll like try to employ our solution and we'll slowly introduce a few constructs and see what happens. So I'm going to pause here and this is where like I'll like wait for 5 minutes and ask people if they're caught up. There are like few fix me blocks. What you are supposed to do here is replace this with actual code and there is, but this is a nice example for just showing concurrency constructs at the same time, not complicating workshop flow. There are of course like amazing ways to do this across machines, but that will like become a distributed systems workshop rather than concurrency workshop then. This is the example. We are going to now walk through this and fix me blocks. I'm going to wait here for 5 minutes and let people catch up. If everyone has like completed their code blocks, we'll go ahead and like maybe somebody can paste their code block once everyone has caught up, and then we'll like look at the solution. I'll just ask, has everyone caught up? If there are enough plus thumbs up, I'll go ahead and like look at the solution. I'm going to wait like roughly 5 to 10 minutes for this, for people to fix this.
Right. Mark, if you're there, let me just paste out code that can help you. So this is just running it 100 times, checking if the first block won or the second block won. So actually, should it be the other way around, but doesn't matter. If you run it 100 times, you'll probably see different counts in both blocks, which just tells you that there was contention. So sometimes you'll see 220 and sometimes you'll see 121.
Hey RHI, sorry, I was AFK for 2 minutes. What
Yeah.
are you talking about?
So I just modified the code a bit to run 100 times and then measure what was the value of A, just to see that there is actually contention. Sometimes it is 2, sometimes it is 1. So
Gotcha. Okay. We can maybe run that code after the second chapter.
yeah.
Hey Wesley, I'm curious what the exceptions were, or where they became opaque, how they became opaque. Ah, okay. So were you running this whole block? Let me share my screen again. Maybe you can like share the code snippet directly to me, so you don't take away the fun the other people, but I can look at it and see why it was causing concurrent exception. Yes, Daniel, that should be ideal, but we'll discuss why it's not also. In some cases, it might not be one, and we'll look at that also. But it will be tremendously lower than what we had seen earlier. It won't be in hundreds. Okay, let me talk about the default a bit. So basically, what we are saying is we are reading from Redis. If Redis is not there, we are saying is the update ongoing. If an update is ongoing, okay, Wesley has figured things out. That's great. Just coming back to what default means here is when an update is ongoing, we don't have anything to show return, because we don't want to load MongoDB and read more from it. So we are just saying default. Another way of saying it is we can ask client to retry. It just says that I don't have any data to give you and you can retry. I think retry is a better name for it instead of default. Right, checking up on people who have caught up. I think we can wait a couple of more minutes and then we can go ahead with the solution. Uh, any one of you who has like caught up can share the solution, and I'll run through that. Just ping me directly on my TM so I can just pick that up and walk through it. All right, let's look at the solution. Daniel has submitted one solution and I'm just going to like paste it in my Emacs. For people who have not been able to catch up, you can like go into the second. There are like more problems, and you can like just keep working on them. That will be in the best interest of the time that we can cover more material, and we'll also talk about how we reached this solution. So I would want everyone to be looking at my shared screen now, so we can like walk through the solution and see why we chose a few things here, few concurrency primitives. All right, so I'm going to like run through the solution that Daniel has submitted. So this is his version of read plus update -2, and he has also used an atom. So if you go back, okay, the obvious choice here is to use an atom because it's just a single register update. Now we are going through the function, and here it's interesting to note that we are just allowing you to make choices related to concurrency. Half of the problem is solved. Here we are just asking you to use the right concurrency construct or mutation at the right place, and that's all. We don't want you to be solving the whole problem on your own. And there are some take-home tasks that you can also look at, but this is here we are just like developing that intuition, right? So here obviously like you're derefing the atom ongoing update say, which is basically what we are holding in this atom is a hash set, and hash set can be used as a predicate. In that predicate, we are passing k, and we are asking, is this update ongoing? If not, do these things, and then you are marking this update as ongoing, and then you are doing your rest of the things, that fetching from Mongo and setting your Redis key, which we did already also. And then you are saying that, okay, I'm done with my ongoing update and just source. If there is an ongoing update, we don't have anything better to do. So we are saying default. This can also mean retry from client, but this can tell client that retry after a while because there is a cache repopulation happening, or like we just give a default value that the UI can render, and that can be like a graceful degradation during this time. So it's a choice that we are making, and we'll see how we can also avoid that going ahead in the second problem. So let's try to run this and see what the output is. Okay, so ideally the calls to Mongo should have been just one, right? But they are four, but that's great. Like there is no call to Mongo. Call to Redis is also quite a lot, right? Because we are now calling it 10,000 times. So this is great, but this is this one like annoying thing, which is like, I'm just telling client that retry your read, right? Which is fine. We have our Mongo intact, and that's a great achievement. But why is it four, right? And we can like argue about what's happening here. Maybe like I'll just wait and let someone answer why the answer to Mongo 4 Mongo is not 1 and 4. Maybe anyone wants to like just raise hand and like take over the mic and talk about it. Any takers? Yep, we can call it kind of like a race condition. James, do you want to talk on mic? Maybe I don't know how I can give you that permission. Oh, okay. Can I unmute you?
Okay.
Oh, okay. Here you go. Hey, James.
Hello.
Okay.
Because the reading
Mhm.
isn't happening atomically,
Right.
multiple threads are seeing that update ongoing is false, and then
Hmm.
a bunch of them swap the same key in.
That is
Sometimes.
absolutely correct. So yeah, you're bang on this when you say that multiple threads are reading that there is no update ongoing, and all of them just like say that, okay, I'm going to like just read from Mongo. And in this case, there were like 4 threads. Thank you, James. So, okay, let's see how we can improve this solution, and can we use something else to like make it better and better. Okay, so instead of atoms, let's say we want to use ref, and there is no good reason to use ref here because it's just a single register, and you can do the same thing with an atom also. I'm just using ref here uh, for like getting you used to using a ref. This can be very well done with the atom also using compare and set. But let's try it with a ref and see how it goes. Again, I'll wait for a few minutes until like we can go ahead again. I'll ask, is everyone done? Question mark. And wait here for a few more minutes, and we'll see how we can use refs here and what all fix me look like. Oh wow, some people are already done. All right. So it looks like a lot of people have like completed the whole chapter, which is oh, this question is for the second assignment, which is read update 3. I'll ask a more pointed question. Is everyone done with? and I'll wait here for like few minutes.
Next
Yeah,
exercise.
yeah, yeah.
Next exercise.
Let me get it from Arnold. I hope not a lot of people have seen the solution. Sorry about that. I am picking up one from Arnold now. All right, so here now we are using a ref. So let me evaluate that. Now, since it's a ref and I want to change it, I'm putting it in a do sync. I'm reading value of it and saying if there is no update ongoing, add a ongoing update. Then going to the ongoing update, do your thing, read from MongoDB, set the Redis key, alter your ref by saying, okay, there is no ongoing update, and then return the thing. But this annoying default thing is still there. But let's see if you have at least reduced the call to Mongo, and hopefully it's down to 1. Yeah, now it's down to 1. Right, as many times as we run, it's going to be 1. But this default thing is still there, right? And what do we do about this? I think kind of Wesley has solved this already, but I'll wait for a while for the read update 4 thing. This again uses ref, but a different data structure now. And based on the data structure and a few things that are happening here, we can other threads which are not actually reading from MongoDB can actually wait for a value. Now here we looked at a construct right at the start of the workshop which helped us talk between 2 threads just past 1 value. And you can go to chapter 1 and see, look for the hint. I'll wait like a few minutes and again add a update here. I hope this will be done already by a lot of people, but let's wait for everyone to catch up. Hello. Okay, so we can continue looking at the solution for read plus update 4. Is going to ask, okay, to go ahead. I think Wesley had shared the solution before. And I'm just going to ask one more person to share the solution so that everyone is involved in solving these problems. Okay, I'm going to just use Wesley's solution because there aren't more pings about the solution. Let's go ahead since I have one more chapter to cover also. So let's take a look at this one. So this is read update 4. So again, we are using a ref, but instead of uh, hash set, we are using a hash map now. Now here we are, I have just like use get, and that is already there in read update 4. But this was the piece of the puzzle which is missing, which is we are going to use a promise. Okay, and I'm going to just associate this promise into the hash map. Okay, and return this also. Right, So what I'm doing here is I'm just saying either if the promise exists in the hash map already, which means this thread or this request has to wait on the promise to deliver. If this thread itself is going to create that promise, then we are going to the update path, and we have a case here, and we are saying, okay, go into the update part, read from Mongo, do your usual business, uh, remove the entry from your ref, and also you're doing a new thing here is deliver the promise with the value of Mongo read, right? Uh, on your wait path on different threads, you can also just deref and wait for it. If we compile this, this actually says that, okay, there was one request to one request to Mongo, and we waited for 2078 request and got the response, and we also read from Redis. There is another one improvement that we can do, which I have left out here, which is, let's say this is a HTTP request, and this wait might take a longer, and I don't want to wait for that long, right? So if you see deref's arguments, right, there is another thing called another signature called ref timeout ms timeout, excuse me, timeout val. What this means is deref the current value for a certain amount of time, let's say 3 seconds. If it takes more than 3 seconds, you can always default to retry client. And this becomes like a complete foolproof solution where you are also saying that, oh, okay, only update Mongo, only read from Mongo from one thread, update Redis. Also, rest of the waiting threads can wait, but also wait for 3 seconds and not more than that, because you might have some SLAs to meet. So basically, in all, in this chapter, we have seen that just by using basic concurrency constructs, and not even like we are not even using co-racing here, we have achieved a lot, and we have solved like this interesting cache problem called thundering herd just by these basic constructs. Okay, so I'm going to wait if there are any questions, and then we're going to go ahead for the next chapter. And the next chapter is going to be a small one, and it is a little open-ended. I'm just going to oh, okay. Maybe Dan, you can share your solution and we can look at it. This is related to read update 4. Let me just copy it here. Pasted. Okay. So you are getting Redis hits all the time. I need to delete few of these solutions. Copy it again. Paste it. This is Dan's solution. What we are doing here is wait or read from Redis.
I think Kapil has dropped off. Let me just ping him. If people haven't read, I think Kapil has just posted saying his laptop has crashed. Uh, just one of these things. So he'll be back.
Hello.
Yeah,
Sorry, people.
Kapil, you're audible. Yeah, you're audible.
It looks like there was too much concurrency for my laptop. I'm just starting up my REPL. I'll share my screen. I think there was one problem that Dan had shared, which did not run as expected, and we can use the last 1 hour to debug that problem. I'm going to just like run through the last chapter, and it has a few problems that we can just look at. Okay, so just going to start up the last chapter, and if there are any questions on this chapter itself related to timeout, we can take them after the break maybe, and just finish running through the last chapter. Does that sound good? Yeah, Wesley, the timeout won't be triggered because it's a big time. Otherwise, you'll have to add a thread sleep somewhere in the update part for the timeout to trigger. It's just like a precautionary thing that we are adding it there. Okay, so the next chapter, I'm not going to run through the problem statements, but the examples. There are like different strategies of the same. This is the same nature that we have solved the thundering herd problem, but this is slightly different. This in this thing we are going to implement a circuit breaker for again MongoDB. Here the intention is even if we get exceptions from MongoDB, and I'm going to use a different method from the same database namespace called fetch1. This fetch1 throws exceptions for some particular cases. This exception also has data which says what is the cause, so it is easier for you to debug if it is the MongoDB is causing the exception or your code. So I've just added the try catch in that sense. The goal here is just for everyone's benefit. A circuit breaker pattern is when your database is throwing a particular exception or a particular indication that it is under load. Mostly it will throw a timeout exception and say during that time, usually the strategy is not let any request go to MongoDB in any case, and just return a 500 or rely on some other database. Now to do this, what is the general pattern is you see a pattern of errors from different threads, basically exceptions. Once you see them, you bump a counter and you say the circuit is tripped after the counter goes above a certain limit. Once that counter is tripped, you don't let any request go to MongoDB. You either say, hey, I can't do anything, or you can just say, just return error. So there are different strategies mentioned here. One is just trip after 20 errors and just be like that, which is not very practical, but we start with that. Then we say trip after 20 errors, but once trip just stay like that for 10 seconds, which means just trip for 10 seconds, then open the floodgates again. There is third strategy, which is trip after 20 errors, which you saw in last X seconds, and then open the floodgates if it is tripped for after 10 seconds. So here, mostly you are going to end up using an atom. The problem statement here is you have to like push a lot of state in that atom and manage that. That is the problem statement here. I'm going to leave it as open-ended, and you can try it out during the breaks or even after the conference. We are going to create a solutions branch of this repository where you like actually put the solutions. You can also reach out to us directly, and like we can discuss the solutions again. I think due to shortage of time, we can't go over this chapter, but everyone has got the gist of it, that what is needed to be done here. We don't need to use refs here, but feel free to use refs also if you feel that is the better way. Also, interestingly, this same problem can be solved using core async also. So after the core async chapters, which will happen after this break, you can also attempt to solve the same problem using core async. So yeah, Arichai, anything to add here?
Not really. I think will Carmen will split for a break now. Is that?
Yeah, if this is a good place to stop, then we can
Yeah,
take our
yeah.
break now.
Okay, cool. So yeah, hope you guys take a break, get refreshed,
Yes.
and after we come back, we'll go over my favorite concurrency tool,
Yeah.
which is CSP and core.async. So
Yep.
thank you.
Yeah, we'll like just break for dinner and I guess breakfast over there,
Lunch
and be
here.
back in 1 hour. Yeah.
Yeah.
Okay, sounds
We'll
good.
be back in an hour.
We'll see everyone in an
All
hour.
right.
Thank
Bye
you.
bye. Thank you.
Hi, welcome back to the second part of the workshop. And this one's on CSP, communicating sequential processes. So in this section, we'll briefly cover what CSP is, how it is useful as a concurrency tool, what is the basic usage of the core.async library in Clojure, what is some of the advanced functionality that core.async provides out of the box. Then we'll look at common concurrency design patterns that are natural to the CSP style of concurrent programming. And finally, I will hopefully leave you off with an assignment where we convert a synchronous series of data transformations into a parallel asynchronous pipeline. So communicating sequential processes is basically a language for describing patterns of interactions. And basically CSP allows you can describe your system in terms of component processes, and those processes are supposed to operate independently and interact with each other solely through message passing communication. So as such, any CSP implementation generally consists of two parts. One is the channels, which is the main construct, which are basically messaging queues with synchronization primitives built in. And then you have processes. So any concurrently running unit of logic that basically reads or writes from these channels is a process. So as a concurrency pattern, CSP is different from what I would call traditional shared memory primitives. So with shared memory, the aim is basically to provide controlled access to the memory by multiple executing processes. On the other hand, with CSP, the aim is to break down the shared memory into data, and then you have to pass around that data between processes through channels and do away with as much shared memory as you can, right? So with that said, uh, let's let's look at some code and let's do a brief walkthrough. Just a heads up, I'll probably turn off my video now because I'm operating on a 4G network now. So let me just turn that off and let me start sharing my screen.
Hey, Arajay, a quick note. I'm just starting a new
Yeah,
thread for this chapter.
perfect. Thank you.
Yep.
All right. So some eager eyes may have noticed a small joke that I was trying to make on the Slack channel. Basically, I was trying to hold off any messages from coming in for 30 minutes. But yeah, anyways. So hopefully by the end of this workshop, you'll know exactly what this line means. Cool. So let's start. So so let's say we want to wait for a value to arrive from somewhere, right? Let's say that some thread just wants to wait for something to arrive, and based on that value or based on the fact that it has arrived, it means that it is safe to go ahead, right? It could this could just be a very simple synchronization primitive. So what we would do is probably use something like a promise, right? So let's say I've created this promise. Now this is the process that is waiting on it, and this is the process that is going to deliver the results, right? Pretty simple. This could be seen as a very naive implementation of a channel, but this is only the reader part of it. Unfortunately, there is no concept of writers waiting on readers to be available here because essentially every action after this, okay. So every action after this first deliver is going to throw it away. So the reader is not going to wait around just because there was nobody dereffing this promise, right? On the other hand, channels offer exactly something like this. So Clojure.core.async is the library that we are exploring today, and that has a very simple function which creates a channel like this. Now let's try. So the basic operations or primitives on this channel are essentially two. One is a put, which you can consider to be similar to a promise deliver, and the other is a take, which is going to read from that channel, right? Now let's see what happens here. Let's see how it is different. So the put signature is you give it a channel, you give it some value, and you give it a lambda to say execute this after your put is successful, right? So let's say if this executes, it did, right? We didn't see a print saying wrote on the channel. So clearly this put has not yet succeeded. But does this work? This does work, right? So what does mean is async.putBang is not blocking your current thread of execution, right? But it is blocking its own callback. Now let's see how you can unblock that callback. The way to do that is to do a take. Now, if you look here, this says wrote on the channel, right? So now because there was somebody who was taking from the channel, the put also succeeded, right? And this is the basic synchronization primitive offered by async channel, right? So now let's say we want to take another value from the channel. Was it available? No. So essentially you didn't see anything being printed here, right? Now clearly there is nothing on the channel, so this take is going to block, right? Now a quick question from the APIs that we have seen so far, can somebody tell me what would go here so that this another value actually prints? You can use that thread if you want for the discussion. Yeah, so James, Michael, both of you are right. Let's just unblock this and let's just write that value. So wrote on the channel, another value, done, right? So essentially what you see here is the number of puts and the number of takes are like, if they are well balanced, then you have an empty channel, right? If any of them, like if you don't have a taker, the putter is going to wait. If you don't have a putter, the taker is going to wait, right? But this doesn't look like too much fun, right? This is a very basic operation on a channel. Let's do something fancier, right? Let's do this. Now this is again another API which says put on the channel and block the current thread of execution and put this value on the channel, right? Now, do you think this, well, we have already executed it, but that's okay. But do you think this gets printed? It doesn't get printed, right? So the reason that it doesn't get printed is because this is a blocking call, right? So the convention in core.async is anything that ends with double bangs is generally a blocking call. So it is going to block the current thread of execution. Anything that doesn't end with double bang is not a blocking operation, right? So what's the corresponding blocking take that we have, right? So quite naturally, this is the blocking take that we have, which corresponds to this blocking put. So let's do this. All right. So done putting on the channel. So this statement got executed because this future was blocked here. but as soon as this instruction executed, the println statement was freed, right? So in this way, a channel can be used as a synchronization point between two threads of execution, right? Now, a subtle difference that I think is important here is what is the difference between an async chan and an async chan 1, right? So if anybody wants to hazard a guess, what would fix this statement? Like, what do you think is going to happen here? Will this let ever return? What will cause it to return? Again, you can use the Slack thread to put in your answers. All right, cool. So I think you have a fair idea. So basically, the difference between chan and chan 1 is a chan 1 channel is slightly more lenient. It will let you add this value to the channel because it has a buffer size of 1. So it can hold one value essentially, right? But if you go and try and write another value to it, it is going to fail, right? So if you do this, you get, like, you basically have your answer, right? So an async chan 1 is slightly different from an async chan. Both of them can hold a value, but the synchronization primitives are slightly different. So something to be careful. So if you don't want like total lockstep synchronization, I think a chan 1 is a good option. All right, so then if you can specify 1, can you specify a higher number, right? So of course you can. So this is the way you create what is known as a buffered channel, right? So now with a buffered channel, what you are able to do is you're able to write multiple values on the same channel, right? So let's say we execute this in a future. So now, as you can see, the first 20 puts on the channel were successful. But do you think the 21st has succeeded? And if not, can you tell me what we need to write here so that this statement gets printed? Yeah. All right. So I think what James has said is correct. So what you do here is you take a value from the channel. So the value from the channel is something, and so the value on the channel is basically 0. So now I was able to put the 21st value. So what you have seen here is essentially a buffer of 20, which has synchronization primitives at both ends. So you can put 20 values in it. You can't put the 21st. The 21st is a blocking operation. And if you take one from it, the 21st will succeed, right? Okay. So now we've seen that we can put stuff on the channel. We can take stuff out of the channel, right? But my application is always slightly more complicated, right? My application actually shoots off 4 operations, and I'm essentially okay proceeding even after one of them completes, right? So now let's say we have a long running operation like this, which starts a future, writes something out, and writes out the function, the output of this function, right? So now let's say I create 3 channels. I create a database channel, I create a file channel, and I create an HTTP channel, right? And then I shoot off 3 long running operations at different intervals of time, right? Now what I want to do is I want to wait till any one of them completes first, right? And the way to do that in core.async is to use alts. So with alts, you have the capability of essentially running something like a switch on a set of channels. So what this syntax means is run alts on these 3 channels and give me the first channel operation that succeeds, right? Give me the first, yeah, so it is like, as you just said, James, it is like a select for sockets. So give me the first one that succeeds, right? So let's compile this and let's run this, right? So you see, since you have random amounts of sleep, you get different values out here, right? So what this essentially means is you have a way to select between multiple channel operations. We will see in a future chapter that alts is actually able to write to a channel also, because writing to a channel is also a channel operation. So that is also possible here. All right. Cool. I will just take a pause here and I will, are we good to move ahead? I will just wait for at least a quorum of people to tell me that we are good to move ahead. We just covered the basic operations of a chan, a put, a take, a blocking put and take, and what's called an alts. Can you make an infinitely buffered channel? No, you can't. And so yeah, you can't. That is the short answer. The long-winded answer is probably it doesn't fit well with the CSP theory, because essential an infinitely buffered channel is the writer doesn't care whether there is a reader or not. So
Michael, do you mean that channel that never blocks on puts and gets, or do you mean infinite memory of buffer? I mean, it's possible for channels to be okay.
yeah,
I mean, with a sliding buffer, it is possible to have like non-blocking puts, but
right.
it's just data loss.
Yeah. Right. So I assumed it from the point of view of having an infinite capacity.
Right.
So,
right.
yeah. All right. Cool. So we probably have 10 people who are saying it's good to move ahead, and it has stabilized in the last 10-15 seconds. So we'll move ahead. So now what we have here is essentially this alts is at the mercy of these 3 long operations. Now, if this random sleep was like this, suddenly the operation has to wait for a long time, you see. Now I don't want that. I don't want to wait, like I don't want to wait for the first operation that succeeds, right? Maybe my rules say that I can only wait a certain amount of time. I can only wait 300 milliseconds. And if any of these operations take more than 300 milliseconds, it's an error somewhere, right? I'm very strict about my turnaround, right? So core.async provides a very good functionality for expressing exactly this requirement, which is known as a timeout channel. So a timeout channel is essentially very simple. What it does is it forces the current thread to sleep for the specified amount of milliseconds, and post that it closes the channel. Now it's a side effect of the close operation that this read from the channel succeeds, because reads from any closed channel always return, right? If that makes sense. So this is not writing anything to the channel, but it is only closing the channel so that any takes from the channel will succeed, right? So let's do this. So you see the current thread blocked for 1 second and then it printed a value. And the function that was actually blocking was this take, right? All right. Is there any visibility? So Eric asks, is there any visibility into the state of the channel? Good question, Eric, and we will come to it in some time. There are ways to do that, but it's not considered mainstream to be using. So what you have to do is essentially do a custom buffer for a channel, and then you can have functions defined inside it to help you see the state of the channel. All right. We have a message from Alexander. Is that a question? Do we like?
He has just shared a blog post about how
Okay.
to like look
Okay.
into.
Okay.
And
Okay. Cool. All right. So then, how do we use this timeout channel? Right. So, all right. As we already saw, a closed channel always returns, and it always returns right away, and it says nothing. Right. Reading from a closed channel is going to give you a nil, but reading from a closed channel always succeeds. Right. All right. So then what about writes? Writes on closed channels don't succeed. As you can see, false is essentially the status of the write operation that this function is returning. So it writes to a closed channel will never succeed. All right. Cool. So now let's do this. You've seen how timeout channels behave. Can you modify this piece of code here to satisfy the above requirements, which is if none of the operations succeed within 300 milliseconds, you have to time out. So I will just wait. Probably I'll wait for a couple of minutes or maybe 5 minutes. And if like, okay, so I am done. Okay. Are you done with your timeout solution? So if you're done with the timeout solution, just give me a thumbs up on the Slack message. And if you already have code, you are free to send it out to me if you want. All right. All right. Is this better, Kapil?
yeah,
In
much
terms
better.
of visibility? Okay.
Yeah.
All right. Sorry about that then. Apparently my font size was slightly small. All right.
I mean, it was still readable, but this is better for
Okay.
like everyone.
Okay, perfect. Cool. So yeah, all right. 6 people have already solved it. Let's just give it a couple of minutes for other people to catch up. All right, let's just pick at random from somebody. Alexander, if do you want to share your solution here? So yeah, Daniel has sent me his solution. His solution is even stricter than the one I had said. He probably cares more about RPS and throughput. All right. All right, cool. So, but the, okay. So let's discuss what Alex, so Daniel has given us a solution, which is absolutely correct. Let's just discuss what Alexander is trying to say. But the idea is you will deref a future which is running an alts, which is timing out. Fair.
This will still have to, like, yeah, it's
This is
fair, I
fair.
guess. Yeah.
Fair. But the more core.async solution, if that is a word that I can use,
I guess you can
is
just say idiomatic from core async point of view,
yeah, maybe
but I like
yeah,
the sound of
better.
it also, core async.
So this is probably a more idiomatic solution. So you create a timeout channel and you just pass it along in the alts, right? But Alexander, your idea was not wrong at all. It's just more what is more idiomatic, right? All right. So as we briefly said earlier, alts are not just for reading from channels. Alts are more intelligent. Alts can support write operations also, and they can support a combination of read and write operations. So essentially what you have here is you have a channel which you want to read from, and you also have a channel which you want to write to, right? And alts can pick one of them for you, and it will tell you which operation succeeded, right? By giving you the return value as a vector, a two value vector, saying this is the value and this is the port, right? When a write operation succeeds, the value is always a true or a false, depending on whether that write succeeded. Alts also has a default option, which says if none of these succeed, just give me a no op. There's nothing happened. And alts also has a priority option to say that treat these operations in priority of the way I write it, right? So essentially what alt says is if all of them are ready, I will choose pseudo randomly. But if I say priority true, then alts will say, okay, I will go top to bottom and I will see which is the first one that is ready, all right? All right. So the way the long running operation was, sorry. So James is asking, when would you get the default value? So, right. So if you provide a default value, essentially there is no blocking uh, because none of these operations are succeeding and default is going to succeed, right? So if you want to look at this, so no matter how many times you run it, you're always going to get a no op because you have provided a default. So you're essentially saying, don't block, take whatever is ready, otherwise don't take anything, right? All right. So let's look at the long operation that we wrote earlier, right? So this long operation is taking a function and it is taking an output channel on which it will return the value of that function, right? A slightly more idiomatic way to do this is, can the function return the channel on which is going to write the value, right? And this brings us to our next question in this chapter, which is, can you rewrite this function, channel operation, in a way that it returns the channel and it returns the value of this f on that channel? So again, I'll give you around 5 minutes. And are you done with channel operation? All right. So if you're done with the channel operations solution, just give me an indication on the Slack thread. And if you want to send me your code, feel free to send it via a personal message so that other people can still attempt to solve that. All right, so Max was talking about the Emacs theme that I'm using. I think it's One Dark, if I'm not mistaken. Ligatures. I pretty much like ligatures, Wesley. So I use ligatures wherever I can. All right, let's go back to our thread and see if people have done this. Again, if you want to send me the code, or if you want your solution to be discussed, probably just raise your hand. I don't know. Yeah, maybe. Just give me an indication and hopefully you'll make it work. All right. James has sent one in. Looks good. Yep. All right. So I am just printing out essentially what James had given me. And this is absolutely correct. So the function creates the channel, it runs a future so that it doesn't block the current thread. Once this function is completed, it writes the value onto the channel and it runs this channel, right? This return is not going to wait, of course, because it's a future invocation. So what did I not do? Sorry. All right. Yeah. So only took a function and it returned a channel on which I can read the output from the function, right? So this is essentially exactly what async.thread provides. Async.thread executes the body in a thread pool thread and it returns us a channel. So if you look at the return value here, it says core.async impl channels many to many. So what you can do is you can do stuff like this. And if you do this and then return this weighted and then return 42, right? All right. So this is an important pattern. We'll come back to this pattern of functions returning channels in our design patterns also, and also in our assignment, hopefully. Cool.
Yeah, Archai, there are two
All right,
questions.
let's look at some questions because
Xavier.
I'm done with my first chapter. What is the difference between using future and using async go? Yeah, so Nick will come to async go. That is chapter 2 material. And it's so hopefully I'll reserve my answer to when we start discussing chapter 2. But there is a difference.
Chapter 5, right?
There is a big difference.
Archai,
Would it
you
be a
mean
good
chapter 5,
practice
right?
to close after, or is that not important here? It is of course important, and we should be closing channels that we own. This is just, I just wanted to keep the code simple for now, and my machine probably will be mad at me for holding on to so many channels, but that's okay. All right, so I'll just give you a couple of minutes for any questions. So are we good for chapter 2? So if you guys tell me that we're good, we'll move ahead. All right, perfect. I can still see some people, but yeah, it's mostly, sorry, true. So yeah, this is what happens when two people are working independently on two things, and then you have to rename files. My mental model has not changed. For me, chapter 2 was what is chapter 5 now.
Naming things is hard.
All right, let's move to chapter 5. All right. So essentially threads are good and threads will probably do in most of the situations. But what if you want something more lightweight? What if you don't want something that holds up a dedicated JVM thread, but it also provides us similar kind of callback semantics, if you will, on channels, right? So this is exactly what async.go provides to us, right? So, sorry. So what we have done here is you can essentially think of these as very lightweight threads, and these are going to execute in a thread pool, and all the channel operations that you create inside Go blocks essentially have to have this convention of just using a single bang instead of multiple bangs, right? So we will come to what it does probably in some time, but think of these as lightweight threads for now. So you've executed this, and now from another Go block, you are writing to it, right? So essentially the same thing as a future. None of these operations blocked my current thread of execution in the REPL, and both of these happened on a separate thread, right? Now, Go blocks in core.async literature are also referred to as IOC threads, and IOC here means inversion control. So the reason behind that is Go blocks are a kind of complicated deep walking macro, which essentially turn your synchronous code into a callback and a state machine, which is attached to a channel, right? So think of this as an implementation of the async await system, which gives you an illusion of having like imperative style of coding one after the other, but and under the hoods, it is converting everything to a callback, right? So what it does is it walks the async go body, and whenever a channel operation is encountered, like a channel operation like this, right? So these kind of channel operations are not to be done inside a Go block because these are blocking. These are known as parking because you park the Go block, you don't block anything, right? So once this is blocked, this basically comes out of the thread pool and stops executing, right? But once the channel operation succeeds, yeah, Kapil, were you saying something?
Yeah, so another way to just put that is when like the put on chan is blocked, right? It is not actually using up a thread. It's
Right,
just not doing anything basically.
correct.
So if you had to do the same thing in a future, you are actually using up that future thread somewhere
Right,
in your stack.
correct. So this is basically what Kapil said is the difference between a park and a block. So park is essentially you take that thread out of the thread pool, it stops executing. It gets attached to the channel on which the channel operation is executing. So this Go block gets rewritten and attached to this channel. Now this inversion of control is crucial, especially for Clojure script to provide an illusion of threads, because Clojure, like JavaScript, doesn't really give you threads, but this kind of callback mechanism can give you an illusion of having multiple threads of execution, right? And just a small implementation detail, I think Go blocks are all supported by one single thread pool, and the size of that thread pool is quite limited. All right. So if you have noticed, when I do this, the Go block also returns something which looks like a channel and is actually a channel, right? But can you tell me, or can you guess here what the value would be that is returned by that channel? So if you look at this code snippet, what I'm doing is I'm running this Go block and I'm trying to read from the channel that the Go block is giving me, right? So can you predict what the value will be from that Go block, the channel that the Go block returned? I see something on the thread. All right. Yeah, so you're right, Ray. The value returned will be 42 because this is the last expression in the Go block, right? But when do you think this value will be returned? Yeah, so just to answer James's question, yes, Go itself returns a channel, and that channel is basically going to give you the last value in the expression of the Go block. All right, so the question was, when do you think this value will be returned to the channel? And all right, just in the interest of hopefully saving time. Correct. So John, you're right. When you take from the parking operation, so the full answer is when all the parked operations succeed, the Go blocks channel will return a value, right? So if I had another async right here, you will have to probably take two values from the channel, right? Same thing. So the idea is simple. You do this. Sorry, this is probably not good. So you do this, and then you say async slash this, and do this, and it failed. Wrong number of arguments passed. Oh, I didn't give anything. I didn't give the value. Hold on. So this future must have conked off. Is it printing those values at the top? I think it is printing those values at the top. Dan is asking us, can you put twice? You can't put twice. That is why probably my REPL is now stuck somewhere. Let's see what is happening. Yeah, I think my REPL is probably stuck. So hold on. Let me just. One of the side effects of showing code like this on a REPL, I'm sorry, the main REPL thread must have died off or something, or it must have blocked. All right, so let's. Yeah, so let's run this. So sorry. So you define the channel here. You have a future which is pending here, and now you have this. Hold on. Let me check what is wrong. Did we predict the value from the Go macro? This wrote 42 to the chan, which means this wrote. And what am I missing here?
Both are puts to a chan. Is that what you intend to do?
Oh, sorry. Wrong. My bad. Of course. And now what is this crying about? Sorry. Okay. So now wrong number of arguments again. Correct. Yeah. So we are now back. And don't you want? Yeah. Yeah. So since this is a Go block, you're right. We have to have a parking take instead of a blocking take. All right, cool. So as you may have noticed, we used these functions instead of blocking takes and puts. These are known as parking operations, and these help the Go macro essentially do its internal magic to rewrite the Go block into a parking operation. All right. So again, maybe we want to take a small break here and see if the pace is good. Are we good? Any questions about Go blocks? What was the correct return value for line 45? I hope line 45. So the correct return value is, I'm hoping 42 is what you're asking, or so the question was, this is a Go block. What does it return? It returns a channel, and on that channel, it writes the last value in its body. So I hope that answers your question, Dan. Again, if you have any questions that you would like to talk about instead of typing it out, feel free to raise your hands here. All right. So let's just look at a couple of things that you have to be careful about when using Go blocks. One of them is, since Go blocks are macros, they stop rewriting code at function boundaries. So if you have a function like this and you want to say, I will always make sure that I call this within a async Go block. This is not possible. So if you do this, you essentially get an error saying you have used a parking operation outside of a Go block, right? So Go blocks have to have operations like this directly inside them so that they can walk the body and park the operations or rewrite the code as they require. So they stop translating essentially at function boundaries. Also, as Kapil hinted earlier, Go blocks are not suitable if you have a large number of blocking IO calls. So the reason for that is Go blocks are basically multiplexed on a limited size thread pool. And if you have blocking operations and you do them within a Go block, you're essentially blocking one thread from the thread pool, right? And that is not a good way to use Go blocks, right? So instead, what you do is you use Go blocks with functions which themselves have a callback mechanism of some kind. So here we are assuming that the HTTP call with callback is going to create its own thread, and it is just going to call this callback once it is done, right? So then this way you have used a Go block and you've used the parking blocking semantics, but you haven't actually blocked any thread from executing, right? So then it follows that you are not supposed to use thread sleep in Go blocks, because thread sleep will again essentially block the thread and no other Go blocks can execute on that thread. So what you should do is you should prefer an async timeout, because again, that will return a channel which you can do stuff like this. So basically you can do this, right? And whatever. This is essentially similar to doing a thread sleep, but this is how you would use it inside a Go block so that the underlying threads are not blocked. All right. Talking about threads and thread pools, one other thing that you may need to be careful about is that you may need to know about is core.async also provides the thread API, which creates a new thread from a different dedicated thread pool. You should probably use this if you have long running or a more dedicated blocking kind of operation. Or if you want a full-blown Java thread, just use a future and use the blocking puts and takes that we saw in the first chapter. All right. So coming to buffered channels. Now, we already saw that there is an easy way to create a buffered channel, right? So if you do this, sorry. What does that mean? So if you do this, this will basically give you a very simple buffered channel of 100 items capacity. So you can write 100 items into it. Reader will have to read 100 items, or reader will have to read the first item before you're able to write the 101st into it. Right? But there are a couple of interesting kinds of buffers that core.async provides out of the box. One of them is a sliding buffer. So think of sliding buffer basically as a sliding window. So what it'll do is, let's say you've done, let's me clear this out. Let's say you've created a sliding buffer of 10, and that sliding buffer you have to provide to the chan constructor or the chan function. Right? Apologies for my object-oriented references. So now what you do is, let's say you want to do this and you've run this. And what has happened is essentially all 20 operations have succeeded, right? Now, in a simple chan buffer, in a simple buffered chan, you wouldn't expect those 20 operations to succeed. But with a sliding buffer, what happens is it basically starts dropping the values that are the oldest written values, right? So if you look at this, the first value that the slider has is 10, because it wrote 10 values. It started to write the 11th value and it threw away the first value. And similarly, it wrote 20 values and it threw away the first 10 values. So this is a sliding buffer. Similarly, you have a dropping buffer. A dropping buffer is what you do when you don't care about the writer giving you new data. You want the reader to process data at its own pace, and if the writer can't be blocked, then you just drop the data on the floor. So if you do this, and let's say the buffer is only of 10 and you're writing 40 values, all 40 values succeed, but the first value is still 0, right? So it wrote 10 values and it started dropping everything that came after it because there was nobody to read from the channel. There are a couple of discussions, mostly about VS Code. Okay, cool. So this is all great, but what if you want to, so we had a question earlier, right? What if you want to read the values that are there on the channel? You want to inspect a channel. That is also possible. So essentially core.async provides protocols which you can implement, and any type which implements that protocol will, like, you can use that as a buffer here to the chan method, right? So this is a typical implementation of a fixed standard buffer with core.async. It has a couple of methods which says whether the channel is full, what happens when you remove from the channel, what happens when you add to the channel, and what happens when you close the channel. And so now let's say we want to implement a transparent buffer. A transparent buffer is a protocol that we create, and let's say it has one function which says inspect, right? What this says is I want to inspect what is there on the channel, maybe for debugging purposes, maybe for collecting some kind of metrics, right? So now what we do is we define our own type. We implement these protocols. Most of them are similar to the fixed size buffer that Clojure provides out of the box. And then we implement transparent buffer. And what transparent buffer does is it basically gives you a seek of the current buffer, right? So let's do this, let's do this, and let's do this. All right. So now we have a way to create a transparent buffer. Now, can you fix these 3 lines of code so that we have the ability to create channels on an inspectable buffer? Just fix these 3 lines of code. And again, I will, are you able to create an inspectable channel? All right. So if you're able to solve it, just give me an indication. Are we there? Is this too fast somehow? I hope not. All right, I'll just ask once again. I've put in a question on the thread. The thread is chapter 5 discussions. Are you able to run, like, are you able to complete this code snippet and create an inspectable channel? All right, Wesley, you're done. James is also done. Let's just give everybody a couple of minutes to think about the solution. All right. Let's, if we want, let's actually do a quick recap of what we are asking. So we have defined a transparent buffer protocol with one method which says inspect. And what we want here is we want to print out the current state of the channel, right? So what we do is we define our own type, which is a transparent fixed buffer, and it implements the buffer protocol that core.async provides, which has 4 methods. And we pretty much copy the 4 methods from the fixed buffer that core.async provides. And we'd add our own protocol implementation, which is if you call inspect on this, I will just give you a seek on the buffer, right? And then we create a function which will take in a long as the size of the buffer, and it will create a new transparent fixed buffer object. And the question is, using these 3 functions, can you create a transparent channel which supports the inspect operation? Yeah, I'm back. Sorry. So we have a question from Daniel who says, I get this exception saying no implementation of the method full. So clearly the object that you're passing to the channel is that I think the code is not happy with what you're passing to the channel. So maybe Daniel, if you want to send me your solution as a private message. And once we decide to move ahead, maybe we can discuss that. All right, let's see what a possible solution would be. Before that, Daniel, if you want to share the code that you had written, maybe we can take a look. Yeah, so yeah, that is pretty much, I think that will fix it for you. So let's do this. And let's do this. Actually, what we want to do is have this here because we want a reference to it later. and do this. Right. So a couple of gotchas here. You want to use the transparent buffer function because that is just a wrapper on top of the transparent fixed buffer. You want to have a separate handle on the buffer because the inspect method is only supported by the buffer object and not by the actual channel, right? There is a slight difference. So you create the buffer, you create the transparent channel, you write 10 values on it, and voila, you have a channel which can be inspected for whatever data is currently on the channel. All right. James is right. We have to define it differently. Another option that's not the best, dot buff transparent chan. Maybe, but yeah, I would probably prefer the more interface style of doing it because, yeah. All right. So this is how you can create custom buffers, and subsequently you can create custom channels, which you can probably add metrics around, maybe, I don't know. Yeah, correct. So Wesley, you're right. Using a different, like, yeah. All right. So this is essentially how you can create custom kinds of buffers and channels. This is just something to be aware of. You will probably not have to look at this at least initially, and mostly even when you have production systems running with core.async, you will not have to define your own channels. But if you want to do that, there is the option of doing this. All right, so then I'll come to the last sort of gotcha with buffered channels, and that is the risk of data loss. So what I mean by that is, all right, cool, good, thank you, Daniel. So what I mean by data loss is, so let's say you imagine a buffer of 20 messages, and uh, meaning your input channel can essentially write 20 messages on the buffer before any reader has to take it out, right? Now let's say there are 15 messages on the buffer and your process dies. Now there are messages on the channel, but nobody is going to process them. The writer probably thinks that he has written them to the channel and moved on, and the reader is now no more there, and channels don't persist. You could do interesting stuff like create your own buffers which can persist, but that's probably an invitation for over engineering. But what you have to be careful about is buffered channels can lead to data loss because of the fact that channels are completely in memory and transient in that way, and they don't survive across process invocations. So imagine having a Kafka consumer, which essentially just reads a message, puts it on a channel for a further down pipeline to consume. And if that channel is now buffered, you suddenly have a data loss because your consumer loop is, if it has auto commit enabled, it is probably going to put it on the channel and move on saying, I have read this message. But since it's a buffered channel, those messages are just on the buffer. Nobody's reading them, right? So just something to be careful about when you're using buffered channels, I guess. All right, let's open chapter 6, but let's take a pause again and see if we are good to move ahead. Are we good to move to chapter 6? Again, if you have questions, please feel free to raise your hands in the Zoom meeting. Right. If you think we are not, maybe we want to spend more time on chapter 5, some of the things that were mentioned, I'll just give you a quick recap. We saw Go blocks, which essentially you should think of them as lightweight threads. We saw the difference between blocking and parking operations. Then we saw some gotchas with using Go blocks. And finally, we saw a couple of different kinds of buffers that core.async provides. And then we wrote our custom transparent buffer, which can be inspected for all the data that is there on the channels. So if you guys have any questions around it, I'll probably wait a couple of minutes and then move. If you need to do thread sleep in a thread, probably not a good candidate. No, definitely not a good candidate. As I said, a better approach or a better pattern is to use timeout, the async timeout function, and then do a parking read from that timeout. So you have this, you have an equivalent of a thread sleep, but now it's safe for a Go block. Cool. So let's briefly look at chapter 6. It's just a small intro into some of the more complex APIs that core.async provides. So again, Kapil has created a thread for us for discussing anything related to chapter 6. All right. So the first one we want to look at is merge. The merge is, think of it like a combination of multiple channels. And let's say you have different channels on which you are receiving data, but you want just one way to consume that data, one loop which will consume that data, right? And that is exactly what merge provides. And merge essentially waits for all channels to be closed. So it will essentially drain out all the merge channels and then it will close, right? So that is the functionality that merge provides. So let's look at this briefly. Let's say we create 3 channels and let's say we are just writing something onto those channels constantly in a Go loop, right? So what we have done is we have created a Go block and we have a loop inside it, which, so what we want to do is we want to wait a random amount of time, right? So this is probably a good candidate for the question that Michael had, right? What would you do if you wanted to do a thread sleep, right? So if anybody quickly wants to give me the solution here, what is the code that is supposed to go into the fix me? Michael, if you want to take a crack. Yeah, so as James has said, async slash timeout is exactly what we need. Now we keep writing to the loop only if our writes are successful, right? So I will just quickly move on without wasting too much time. So what we are doing here is if our write to the channel has succeeded, we are recurring, right? So this is just a loop which keeps writing to the channel constantly after sleeping for a certain amount of time, right? So this is the function. Now what we have done here is we have given the merge function a vector of 3 channels that we created earlier. And this is again, surprise, surprise, this is again a channel. So the merged is also now a channel, right? So now what will happen is merge is a channel that is a combination of all these 3, right? And what we want to do is we want to write a consumer for that channel, which is essentially going to read, but only read till we get non-nil values, because when we get a nil, that indicates that the merged channel has now closed, which further indicates that all the previous channels have also closed. So Hold on. Kapil has just.
No, you can ignore that message. I'm just linking
Okay.
between
Okay.
two
Okay.
chapters.
Okay. Okay. Cool. All right. So the current question that we are tackling is, can you write this piece of code, which will essentially keep writing to the, which will keep reading from the merge channel until we get non-nil values. All right, so let's just paste in the code that James has provided to us. When you are able to read a value from the merge channel, you recur, right? So this is our infinite go loop, and of course I have not evaluated something. So this is our loop, which is essentially, you can think of this as consumer loop for the merge channel. Any benefit? Sorry, let's just take the questions in order. So Dan is asking, will the merge channel close when you take it and it fails? It fails how? I'm not sure what you mean by it fails. But the merge channel, all right. If let val, read val recur. All right. Oh, so you are saying you are explicitly going to close the channel if you don't get a value from it, right? I'm assuming that is what you mean. You don't have to do this because merge will take care of closing itself whenever all the channels are closed, whenever all the source channels are closed. Christian is saying any, yeah. So Wesley has just answered. Thank you, Wesley. There is no difference between a go loop and a go and then a loop. All right. Cool. So where were we? We had just taken James's answer and created the merger. Now let's define this trigger merges. Let's run trigger merges. And so we actually haven't printed anything. So maybe what we want to do here is do something like this, which will give us handle on the value and redefine this. All right. So now you see data coming in from all three channels, right? So all three. So what we are doing is we are writing channel 1 inside channel 1, channel 2, and channel 3, right? So, and we are only reading from one channel, but we are getting data from all the channels. Now let's see what happens when we close channel 3. When we close channel 3, we start getting only channel 1 and channel 2 messages, right? Now post this, there is no channel 3 message. Now if we keep doing the same thing for the other ones, let's close this. Now we'll start getting only messages for channel 2, and let's close out channel 2, and we'll basically exit the merger function, which was our loop, which was reading from the merged channels. All right. So this is a simple but quite effective API for when you have a stream of sources of channels and you want to treat them or you want to read them in the same loop or read them from the same channel, right? All right. Just a small pause for any kind of questions. Do you guys have questions? All right, we are 10 minutes away from a break. All right, cool. So If we don't have any questions till now, maybe we can move ahead. Just a question to, sorry. Yeah, just a question to Carmen and Nick. What is the duration of the break that we are having now? And when?
I believe it's 30 minutes, Arajat.
Yeah, it's 30 minutes.
Okay, cool, great. All right, so I'll just finish off this chapter in the interest of continuity, and we'll probably look at something interesting when we come back. All right, so using channels and using just the APIs that core.async provides, we can even create a pub subsystem, right? The basic construct that we need is known as a publication, and the publication basically takes an input channel and it takes a function, right? And think of this conceptually similar to a multi-method. So this is essentially a dispatch function on the publication, right? This function will run on any input message that is received on the channel. So what you do is you create a publication, and to use this, you need to add subscribers to it. So what this looks like is a publication holds an input channel. An input channel holds an input channel, and it has a routing function. And based on the routing function, you either output it to channel 1 or you output it to channel 2, right? Now let's create some channels that we want to use as these output channels to the publication. Let's think of these as subscriber channels, right? Now what we want to do is, if the routing value is alert, we want to subscribe it to the alerts channel. If the routing value is audit, we want to subscribe it to the audit logs channel. And if the routing value is analytics, we want to subscribe it to the analytics output channel. So I'll give you some time, and if you guys want to attempt how to do this, I will just open up the documentation of sub. So what sub says is subscribe the channel to a topic of a publication. It takes the topic, and it takes the publication, it takes the topic, and it takes the channel. So using this, if you guys quickly want to tell me what these three functions need to look like, we can wait a couple of minutes. Does anybody have an answer here? We'll just, if you guys have an answer, we'll probably discuss. Okay, Sam has given us the answer. Absolutely correct. So let's just copy his answer, put it here. So what you want to do is you want to call sub. You want to give it the publication that we created earlier. You want to give it the value on which to route it to this channel. And of course, you want to give it the channel, right? Now, what you want to do is you want to keep reading from the channels until you get a nil. This is a fairly simple construct that we saw earlier. So let's just copy it and do like, sorry. Let's just copy it and put it here. So here you will read from alerts. Here you will read from audit logs. And here you will read from analytics. All right. So now we have 3 go loops, which are going to each read from these topics and print the value that you get. And if you don't get a value, you exit out of the loop. All right. So let's, hoping that, okay. Let's run these. All right. Now, what you want to do is, essentially your input channel still remains the same, right? Your input channel is still the channel on which you created the publication, right? This. So anything that you want to write is still going to go into the input channel, right? So now if you do this, what happens is you essentially got a message on this channel. Now, just to prove that, you can do this, right? And now what is happening is it is actually alternately choosing because I have run the same go loop twice, right? And now if I do this, it will probably keep choosing between different ones, which is kind of weird, but that's okay. Yeah, so you see these three messages because I just compiled that same, ran that same go loop thrice, but that's okay. You get the basic idea. And yeah, so this way you essentially have you have created a pub sub mechanism where you put stuff on the input channel, and based on some routing function and its output value, you can route it to different output channels, right? Yeah, you're right, Ray. These are side effects. All right. Cool. So this is the basic usage of the pub sub API that core.async also provides. There is also a couple of interesting other kinds of APIs that core.async provides. If you don't use this in a go loop, that always recurs. Clojure sub, yeah. All right, so there are a couple of other interesting APIs that core.async provides, particularly the mult system and also the mix system, which is all right. We have a question from James. Do we close the sub channel or the sub itself? Does the sub get closed if the pub gets closed? Yeah, so let me answer that one by one. Do we close the sub channel or the sub itself? We can do an unsub, as you said, and then we can close the sub channel. And do the subs get closed if the pub gets closed? Yeah, so let's look at this. I don't think the sub gets closed. You probably have to close it yourself because there may be something interesting there. Maybe let's find out. As far as I know, I think the subscriber channels will need to, actually, let's see. We have a REPL working. Let's do this. Let's close the input channel. And is there a way to find out? Let's see what this returns. Yeah, so I think closing the input channel is closing the output channels also in the subscription. Yeah.
By the way, sub takes an extra argument, which can let you not close it if you want.
Yeah. So that was the correct. That was the other rarity of closed sub that we saw here. Correct.
Yep.
Yeah. All right. Cool. So yeah, these are just some of the APIs that you can use. There is also an add mix API, which is similar to a merge, but it lets you do more interesting stuff while you're merging the inputs from different channels. It lets you selectively mute a channel. It lets you selectively just like uniquely give permissions to one channel to take an exclusive lock saying only you can read from it for some time and stuff like that. So if you're interested, you can go read that, or you can look at the bonus chapter that we have. I've added an example of how you can use the add mix for creating a simple kind of logger where you can selectively just stop info logs or debug logs if you're really interested in looking just at the error logs, right? So a simple toy example that we can use. All right, so this brings me to the end of chapter 6. Hopefully this was a good start. And Carmen, do we probably want to take a break now?
Yeah, it's a good time for a break now. We'll come back in 30 minutes or so.
All right. Yeah, thank you guys. See you in 30 minutes, and we'll probably look at some design patterns that are natural to the CSP style of concurrent programming.
All right, see you around. Bye-bye.
Bye. All right, cool. So let's resume. This is the second last part of my workshop on core.async. So we'll just go over some, for lack of a better word, some design patterns that are generally recommended with a CSP style of concurrent programming. Some of them come from Go's concurrency patterns. Some of them come from just what core.async provides. So before we move on though, just a word of caution. Let's look at our friend deadlocks, and we've seen quite a lot of interesting concurrent code with core.async, and there is a tendency to think that, does this mean that I never have to worry about deadlocks again? And well, the short answer is no, because by its very nature, the concept of blocking reads and blocking write means that channels are also susceptible to a deadlock. So if you look at a contrived example here, we have 3 channels, we have 3 go loops.
Hey, RHI, your screen is not shared.
Oh, it is not. Sorry.
Are we discussing
better?
chapter 7?
Yeah. So we have just started chapter 7, and
let me start a thread.
Yeah.
Yeah, here you go.
All
You
right.
can start.
Cool. So as I was saying, deadlocks are still a very real possibility with core.async channels. And if you look at this contrived example, we have 3 go loops. What they are essentially doing is, one is reading from a channel and writing to another channel, sort of like a forwarder, and it is recurring. And similarly, we have a second channel which is reading from C2, putting into C3, and taking from C3, putting into C1. So essentially, all of these channels are waiting on each other. All of these are parks, and nothing is basically going to go ahead. Interestingly, if you want to kind of seed it, then one way could be to take this channel out and externally put a value on it, and then just watch as 3 go loops keep sending information to one another. There is actually a demo that Rob Pike gave some years back, I think, which is like, he called it the Chinese whispering gophers, where he just had a series of, I think, 10,000 Go routines just sending data to one another. So, but yeah, deadlocks are still very much a possibility. All right. So then moving on to some design patterns. Generators are basically a pattern in which functions return the channels on which they will give data. And there's something that we've already seen. So let's just quickly go over the code. So let's say you have a function which fetches something from a URL and it returns the data that the URL gave you. Now, let's say you want to turn that function into stream of data that you can add a channel on, right? And process asynchronously. So one way to do that would be the fetch takes a channel on which it will write the output. Let's say our example says that you want to fetch it 5 times and then you're done. So a simple implementation here would be to do this, which is to say for 5 times fetch from the URL and write to the channel, right? And all of this is good. All of this, let me just compile it. Sorry. All of this is good. This works. Now let's run a test. In the test, what we are going to do is, sorry, let me just, yeah. So in the test, what we are going to do is loop and call this fetch function and loop on the output channel and see what data we get from the server. All right. So, and as we said earlier, when we get nothing from the channel, we just say we are done, closed. Thank you. So if you look at this, what you get is you get 5 data packets on the channel and then suddenly nothing, right? And why this happens is because nobody actually called close on this channel, right? Because the function which was controlling the stream of data, which I would call this function, or the owner of the channel, isn't the one who owns the channel. So a couple of solutions here, maybe just if your code can allow it, maybe just close the channel here. But a better pattern is for the function itself to return the channel and close it out when it's done, because this function knows when the stream is going to end. Maybe it is ending on an exception, or maybe it is just ending due to some special value that you get, right? So this is a better pattern. Whenever you have a function that is streaming data, just that function returns the channel on which you can read data, right? Another pattern that we actually saw in chapter 6 was the fan-in pattern, which is you have multiple channels. They are going to provide data streams to you, and you just want to merge them and treat them as one data stream, right? So that is known as the fan-in pattern. So again, a couple of ways that you can actually do that. So let's just see what is the best way to. So Eric is asking what is the best way to debug channel leaks. By channel leaks, I'm assuming, Eric, you mean channels which are no longer used and are also not closed, right? So yeah, it is like, I off the top of my head, I don't know a tool for just detecting channel leaks, but they'll probably just be treated as any other object which follows the same GC rules as normal Clojure values or Clojure objects, right, Kapil?
Yeah, I'm not quite sure what Eric means about channel leaks. Maybe we can give him the mic and he can discuss it better.
Yeah.
Can we do that?
Yeah, so he okay, so he means unclosed channels which are just around. So yeah, I think my answer sort of holds. They are just subject to the same memory rules that other objects are. If there is no reference to it, nobody's holding on to it, they'll just get GC'd. And
But
yeah.
I think they're like just like there are a lot of pain points to it.
Yeah.
With any unclosed channel which are not used, like it can cause a lot of problems in some other part of your system, and there is no good tooling to like identify that also.
Correct. All right. I hope we have answered that question. All right. So moving on to the fan-in pattern that we were looking at. So there are a couple of ways to do fan-ins. One of the ways that we can do it is by doing the merge function that we just saw in our previous example. Another way that we can also do it is by using the alts, because alts is going to give you data from any of the channels that are available. It is sort of like a merge, but it suffers from the side effect that alts always keeps returning from the closed channel. So here, if you imagine C1, C2, C3, and if one of them closes, then alts keeps returning the same channel. So you don't really have the same kind of semantics where you can wait on closing of all the three channels, right? So a better fan-in pattern is to use the async merge function. Similar to a fan-in pattern, there is something known as a fan-out, and the fan-out pattern basically says that imagine like you have a set of processor threads, and you have data coming in, and you want to essentially process those messages on any of the threads that are available, right? So you have one input channel and you want to fan it out to multiple output or processor channels, right? So let's look at how we can build such a pattern. So let's say we have a process which takes an input channel, and this is just a PID to basically recognize the channel, right? Now, yeah. So let's do this. Now let's create a simple channel. Let's call process on it, and let's send it a message, right? So now what happened is this channel, this process function received a message 42 on processor 1. All right, simple enough. So now let's create a system which has one input channel and it has three processor channels, and let's start our processor loops. Now, as we looked at earlier, alts also has a variant in which you can actually attempt to write to any of the available channels, right? So that is what we can use here. What we can do is we can just say, so this is the way you essentially give alts a writing operation. You give it a nested vector where the first is the channel on which to write and second is the value. So what alts will do is it will attempt to write on C1 the message M, or it will write it on C2, or it will write it on C3. So this is essentially the step where you are fanning out from one input channel to multiple output channels, right? So let's say you do this. All right. So now what we have is we have an input channel. It is connected to three output channels and three processors, and any of that processor is free to process the message that is coming in from the input channel, right? So if we do this, what you see here is you see a distribution, right? You see message received on the first channel, then the message received on the second, and then the third. And this just goes on in a random order decided by this alts step, right? So this is one way to sort of distribute the load that is coming into an input channel into multiple processor pipelines. And I believe somebody was asking how how we can use this in an actual production environment. We use this kind of pattern in one of our services at HelpShift. So this is served us well. So this input channel is written from a Kafka consumer loop. And these are processors which essentially go out to third-party APIs and forward those messages after doing some internal processing. And yeah, so this is a pattern that we use at HelpShift currently. So now what happens here is, imagine that the rate of messages on the input channel is far greater than the processing capacity of the three processors, right? Imagine that these processors actually have to go out and do API calls, right? So this sleep is probably even like this delay in every processor reading the next message is probably going to be variant, and it is going to be larger. So what happens is, so let's say we define a slow processor, right? And we do the same function, but instead of doing process, we just call slow process, right? And now what we do is, just for the sake of this example, we want to see when does the processor pipeline stop keeping up with the producer, right? So let's say what we do here is we do async timeout and we say 500, right? So now what we are essentially saying is write to the input channel, and if 500 milliseconds pass before any of them can read it, we are saying that the consumers are basically saturated and we can't really do anything, right? So let's try and run this. Now let's do our old future of just writing the jobs. Let me just clear this out first. All right. So as you can see here, you saw here you got that log saying consumers can't keep up, so we are exiting, right? So you wrote probably 11 messages, and after that the consumer just was waiting for more than 500 milliseconds, and it just didn't get any processor that could process the messages. All right. Okay. So the way, sorry. Okay. Yeah. So let's just probably take a pause and before we proceed, and I will just put this on the thread. All good so far. Any question? All good so far. Okay. So let's just take a break. If you guys have anything you want to discuss, or we can just move ahead. So. All right. So what do we do in such a case, right? What do we do when our input or our writers are too fast and the consumers can't keep up? So one of the ways to solve this obviously is to use buffered channels, and this just gives us more headroom in terms of the writer being ahead of the readers in that pipeline, right? So more messages can be put into the buffers, and the processors will get more time to read those messages, right? But as you can imagine, even this will have its own limits, and there will be a time when the buffered pipeline is also going to be saturated with messages, and the writer has to wait, right? So my recommendation here, or something that we have found, is doing something like this, where you're saying if it's not able to write, just exit, is probably not a good idea. What you can do is take that back pressure. Essentially, it is known as back pressure. So hold off the writer until the readers can catch up, because otherwise there's going to be a data loss, right? If something goes wrong, if the system dies, there's going to be data loss, and you can't just have an unbuffered scenario where the writer is just writing messages and there's no feedback to the writer from the readers, right? So
just to highlight here more why there is data loss, uh, we have 3 buffers with each being capacity of 10, right?
right,
And if
right,
your writers keep writing to it, and this is a service, right? This is a production service, so it can like
right,
go off or like shut down at any time. Now there is another problem that you have to maintain is whatever you have consumed from somewhere, you have to also persist those buffers in a
hmm,
file or somewhere else. So it becomes one more problem that you are taking on to yourself instead of just saying create a back pressure from whatever queuing system or whatever data source you're consuming from. So in some cases, actually, co-racing by default is allowing you to create a back pressure, which is a good thing,
yeah,
unless like there is a good reason to like have a buffer.
correct. So yeah, I think the general recommendation here is start with unbuffered channels, and if your system can't take that load somehow, then maybe think of adding buffers into the channel, right? All right. So then moving on to another interesting pattern that we see is something known as quit channels or done channels, right? And this is one of the ways to handle early termination of some kind. So now let's say you have a long running processor loop, and that is based off a core.async channel. This is the producer loop. This is the processor loop, right? So read, but only while the channel is open, right? So let's use our old friend when sum, and what this process will do is until that channel is not returning a nil, you read and you sleep a random amount of time, right? Now let's say you have a function which starts the processor, right? A similar pattern to something that component does, right? A start and a stop method and stuff like that. So let's say you have a start processors function. Now what you want to do is you want to have a stop functionality also, to say that just go and stop the processor loop. Maybe there's some problem in the system, maybe uh, like some exception has occurred and we just want to stop the whole system, or maybe it's just a clean shutdown, right? So what you want to do is you want to stop the processors. So a natural way to think of doing this would be just to say, I'll just call close on the channel, and that is a good way to call stop, because this line here will read a nil and then it will exit, right? So let's see how this works. So we start the processors, we write 30 values on it, we just give it some time for the system to run, and we stop the processors, right? So yeah, so as you can see here, we explicitly stop the processor, but our messages are still being processed, right? So this is kind of a side effect of the way close is implemented. So if you go and look at the documentation for close, what it says is that, of course, the channel will no longer take any values. So any puts are going to fail, but the data in the channel remains available for taking, right? And this is available for taking until it is exhausted, after which any takes will return nil. But if there are any pending takes, they will be dispatched right away, right? So here, what is happening is this is, yeah. So this loop is putting values into the channel, and since it is a buffered channel, this function is just going to, like, it is going to still keep taking values out even after close has been called, right? But if after close has been called, this this blocking take is called, any pending take is called, then you essentially get a nil. So what I'm trying to say is there is a slight difference between a pending take and a take which is being called before the close in some way, right? So to get around this problem, what you want to do is to have early termination, right? So for early termination, what we do is we provide a stop channel to the processor loop, and whenever we so maybe if you guys want to take some time and write the code in this fix me. So what we want to do is take a stop channel, and whenever there is data on the stop channel, you essentially just want to get out of the loop, right? So if you get data on the input channel, you process it. Otherwise, you got data on the stop channel and you just exit out. So if you guys want to maybe attempt that answer, I'll maybe give you 5 minutes. All right, so I've just put a question on the chapter 7 thread. If you guys have solutions, just let me know there. If you guys want to send me code, you can do that. Maybe we can discuss one of the solutions. Yeah, sorry, I'm back. Okay, so can nil be sent through a channel? Is there a way to differentiate return from an explicit nil message?
I believe nils
right.
are not allowed, right?
Yeah, nils are allowed. So let's just do that. Let's just yeah, sorry. Yeah, so there you go. You can't really put nil because that is how you. So essentially, it just indicates the close on the channel. So I think that is why they have added that protection in. All right. Any other anybody else who wants to attempt a solution? All right. Cool. So yeah, I think Wesley, you're spot on. And Arno, is that the way you pronounce your name? I'm sorry if I got it wrong, but yeah, that is a typical use case for an alts. So if you do this here, what you essentially have is you keep reading from either of these two channels. If you get it from the in channel, you process it. But if you get it from the stop channel, you say we have been stopped. This is an early exit. And another interesting thing that is also used is the same process. Like if it's a long cleanup, right? Let's say the cleanup itself takes some time. then the process itself again writes to the same channel to say, okay, my cleanup is now done, right? So the way this can be used is, let's say we do this. And now instead of just calling close, what we are going to do is we are just going to send some data on the stop channel, right? In the stop processors method. All right. So let's say we have defined this. Now we run the same code essentially. We start processors, we write 30 values on it, we sleep for a second, and we just call stop, right? Yeah. So now what we have is, so another, I think I missed this part, is a small addition that you can wait for the process that is being stopped to give you an act to say, okay, my work is done, right? So I told you to stop and you told me, okay, my work is done, right? So yeah, so this is one of the ways in which you can use, maybe just as Arno has said, just think of them as control channels into like these kinds of long running process loops that you have, right? So this is another pattern that is typically used.
Bit of shameless plug here. The talk I have at like this conference also talks about this, and it extends the idea to even think about the whole go loop as a state machine, where it changes states based on the control channel. So you can check that out
Right.
also if you're curious about this pattern.
Yeah. All right, cool. Let's just take a 5-minute pause, I think, before we move on to the final chapter.
Yeah.
And that chapter is just basically an assignment, which you guys can try out. I'll just explain the assignment to you, and I'll just give you a brief walkthrough of the starter code that we have added in the repository. So are we good to move to chapter 7? All right, so if we are good to move, let me just let me know. Move from chapter 7 actually. All right, cool. I think we have an active number of people who are responding and saying we are good to move on. So lastly, I just wanted to discuss the assignment that we have, and maybe you guys can take the time and maybe share it with us over next week. Share your solutions, and we can there is a starter code, but feel free to ignore parts of it or ignore it completely if you want to write your own solution from scratch. So the assignment essentially goes like this. Imagine there is a source of data which is delivering weather related data from different IoT sensors. Now this data is mainly of 3 types. We have temperature, humidity, and wind. And this data is coming from 4 locations. Now this data is also protected by some HMAC signatures just to make sure that there is no modification of data in transit. And it is also NIPI serialized because we want to, one of the things that we want to do is also reduce bandwidth usage, right? So another bandwidth reduction that we are doing is the keys in the maps are compacted. So if you see a :S, it actually means source. If you see a :L, it actually means location, etc., etc. So what we need to do is there are a series of steps that every data packet has to go through, and we have to do these things. We have to deserialize the data. We have to make sure it is authorized. We have to transform the data to make it more readable. We have to run some kind of validation. So for example, let's say wind speeds cannot be negative, humidity cannot be more than 100, and stuff like that, like some kind of validations, right? And then we want to send it off to different Kafka topics, or whatever you want to do at the end of the stream, right? This could be any operation that you want to do based on the type of data that you're getting, right? So for an implementation of all these steps, you can take a look at the CSP util namespace. So the initial version of the solution looks like this. Quite typical. You get data and you thread it into this pipeline to say deserialize first, then authorize, then populate, validate, and then stream, right? Now, what we want to do is we want to modify this this series of operations into an asynchronous parallelizable pipeline using core.async channels, right? That is the assignment. So there is a quick starter thing that we have given to you. So the first step that we want to do is whenever we want to convert an original. So before I move on, just let me just is the problem statement clear with you guys? Are we good to move ahead? So is the problem statement clear? All right, cool. So yeah, so I think like if you really want to be adventurous, you can probably just ignore all the starter code that we have here and write your own pipeline. But this is just some code that we thought would help you to move along. So essentially what we want to do is first a step that we are probably familiar with is convert any kind of data source that you have into a channel. So this is the data source that wraps over this make data function, and it essentially just loops, calls make data, and hopefully does something to the channel, right? So what we are doing is converting this piece of functionality into a stream of messages that we can process, right? Now let's say how do you want to specify the shape of the pipeline, right? A simple specification could just be to say this is the number of this is the parallelization that I want in this stage, and this is the function that I want to run, right? So if you get a specification like this, it essentially means you want 2 processors doing increment, then you want 3 processors doing decrement, and you want 4 processors or threads or whatever you have doing filtering, right? So this is kind of like what one of the shapes of the pipeline could look like. So you have an input channel, it gives or spreads out the data to the next stage, which is a set of channels, and those channels or those processes are running these functions. Then you want to merge them again back into one channel and then move on to the next stage, right? And finally you have the output channel. So so yeah, this is the main pipeline function. I think you can just read through the comments and hopefully you'll be able to figure out what these fix me's are. And I'll just introduce this function because it is sort of important, because what we are doing is in this case, in this stage of the pipeline, what we want is we want a function which can just read from one channel, transform it somehow, and then write it to an output channel. So this should be fairly straightforward to write just as a standalone unit, which is read from an input channel, apply a function, and write it to the output channel, right? And finally, when you run it, the pipeline could probably look something like this, where you have two processes which are doing deserialize, you have two which are doing authorize and stuff like that, right? So again, there are a couple of things that just make the problem interesting. Like if you want to just look at like, are these actually happening in parallel, right? If you are able to write these out, is it actually all of it happening in parallel or not? So there are just some utilities that you can toy stages that you can put in just to see whether this is actually all happening in parallel as we are saying, right? All right, cool. So I will just let you run through these. There are a couple of improvements that we are suggesting to the original function. Stuff like adding exception handling, then adding channel closes, right? How do you handle the input channel being closed? And how do you percolate that close operation down to the output channel, right? That is also an improvement that we are suggesting here. And finally, something interesting is this kind of pipeline pattern is so natural that core.async actually has a built-in function, and that built-in function is also known as pipeline. And of course, it takes transducers. So this is the pipeline function. This is the parallelization factor. How many processes do you want in parallel? This is the output channel. This is your transducer. This is the transformation function, and this is your input channel. So think of this as one stage of the pipeline that we actually implement here on the top. But yeah, just something for you to try and check out. Like, can you build the same kind of interconnected pipeline with just using core.async pipeline and some transducers? So yeah, this is the logical end of my talk. Kapil, anything you want to add?
No, I think this exercise is a great closing for the workshop. I think that will keep people busy with core async and concurrency constructs, at least for a while. So we are going to like push another branch for solutions in a few days. So you can like compare your solutions with this. Even if you lagged behind in one of the chapters, you can just switch to that branch and check the solutions.
Cool. Thank you, guys. Thank you for listening to us, and thank you to the organizers for giving us the opportunity to talk. Honestly, I'm still just getting started with Clojure and all of the intricacies and complexities, but so far I'm loving it enough to the point where this is the first time I'm participating in a conference as a speaker. So yeah.
Thank you. This is like not a very small workshop duration, 5 hours is long. So thank you for like showing patience through of it all, and thank you for the organizers to like make it work so smoothly.
Yeah. Cool. Nick, Carmen, over to you guys now, I think.
Yep.
Thank you. That was absolutely fantastic. And yeah, as everyone's saying in the chat, thanks so much for doing a 5-hour workshop. It honestly was very useful.